And let's welcome Professor Alonso Contreras, which will talk about guided modes in optical PT symmetric waveguides.
Okay, I'm going to talk about guided modes in optical PT symmetric waveguides. And this is a work done in collaboration with Jakubský. Jakubský works at the Department of Theoretical Physics in the Nuclear Physics Institute of the Czech Academy of Science. And I am working right now at Cinvestav Académico in Mexico City. So the idea of this presentation is to present a framework to construct exactly solvable models of optical settings with complex index of refraction. And well, to do that, we use first an approximation for the Maxwell equations that is called the paraxial approximation. And after that, after we have the paraxial approximations, we use the technique called supersymmetry or intertwining relationship. Okay, or Darboux transformation. I am going to discuss theoretical aspects of this construction, and I will illustrate the results with waveguides, but it is not exclusive to waveguides. Okay, let me start with what is PT symmetry. So PT symmetry is something that I think was discovered in 1998. People noticed that some non-Hermitian quantum Hamiltonian had all its eigenvalues real. So they started to ask, can we use them in the similar to Hermitian Hamiltonians? And they asked in particular to Carl Bender. Carl Bender is a professor working at Washington University in St. Louis. And he had a partial answer for this. He started to classify the Hamiltonians with real spectra. And he noticed that these two operators were important, P and T. The first operator, P, is a parity operator. It changes x to negative x, and the derivative of x to negative derivative of x. And the time operator, well, the T operator, is a reflection in time. What it does, it changes I, the imaginary unit, to negative I. So the momentum operator changes to negative momentum operator. And his conclusion, or his first conclusion, was that if a Hamiltonian H commutes with the PT operator, we call this Hamiltonian as a PT symmetric Hamiltonian, and also if its eigenvectors are also eigenvectors of the PT operator, then all the eigenvalues of H are real. And they started to question, okay, can we have a family of non-Hermitian Hamiltonian with real spectrum? Can we use them in quantum theory, or can we use them in physics? We don't have an answer yet, I think. Well, we don't have an answer for quantum mechanics, a complete answer for quantum mechanics, but we do have an answer in physics. So this happened in 1998. 10 years later, they made the first experiment, and here I want to add a parenthesis. We do need quantum cryptography, because right now we can get some emails that we shouldn't get. For example, this one. This is an email sent to Carl Bender. Some professor, well, Demetrius Christodoulides, sent an email to Carl Bender saying, hey Carl, we have some good news. One student saw a PT symmetric system, and he had the experiment. He realized this PT symmetric Hamiltonian. And we can see, well, and he said, okay, we are in close collaboration with other people, with other teams, and they are improving the experiment. We will have soon some results, and I like this last part. So far, everything is done on a shoestring budget. All the best, Dmitry. Sorry. Okay, let's talk about the experiment. In quantum mechanics, we have the time-dependent Schrödinger equation. I want to emphasize this potential depending on x and t. In optics, we can model, well, in some situations, we can model light, or we can reduce the Maxwell equations to only one equation, which is this one. This is light traveling in a medium. Over here we have changes in the diffraction index. And z is the propagation axis. So we have light propagating in the z-axis, and we have changes in the index of refraction. We can see that it's exactly the same equation as in quantum mechanics, but now z is t, and the potential is the negative of the changes in the refraction index. I added here this 0 because this is an approximation, it's an expansion in series, and this is the order 0. If you want to improve this approximation, you go to the next order and next order and so on. So the experiment goes like this. They have two waveguides. It's an homogeneous medium. Well, it's a medium with this index of refraction, the red line. First we have a maximum, minimum, a maximum, and minimum. And light travels inside these waveguids in the following way. If you inject light in one of them, the light will couple with the next fiber. We can say that this is a fiber. It goes to the next fiber, back and forth, back and forth. If you start in the other end, the light will travel, well, back and forth in both fibers, or in both wavelengths. Now, if we have a complex index of refraction, here we have the green line is the imaginary part of the index of refraction. We have a positive section and a negative section. The positive section is associated with gain of energy, and the negative section is associated with loss of energy. So they repeated the experiment, and they have a similar behavior, light going back and forth, back and forth, back and forth. And they use light that is eigenvector of the PT operator. If you choose light that is not eigenvector of the PT operator, all the light goes to only one fiber, or only one waveguide, and it saturates because it's getting more energy and more energy and more energy. The experiment is this one. You have the medium right here. Over here you can inject energy. In order to model gain and losses, they added a mask right here. Then the signal, when they send a laser, so this is the signal, and at the exit, they take a picture, and that's it. So we noticed that a lot of people were working in this topic, but all their changes in index of refraction were in one dimension. And the question that we wanted to answer is, can we construct some exactly solvable PT symmetric potentials or systems where the changes in the index of refraction depend on X and Z in a non-trivial way? And, well, long story short, the answer is yes, we can. So I'm going to show you how can we produce this. So we start with a system that we know how to solve. In particular, I'm going to use the free particle. So this potential is 0. In optics, that represents a light beam traveling in an homogeneous medium without changes of index of refraction. And we link this system with a new one that we don't know yet, using an operator, this calligraphic L, and we don't know yet this calligraphic L. If we are able to find this calligraphic L, we are going to be able to find S1. And if we know L also, we can translate the solutions of the free particle to solution to our system. So we will know the solutions of the new system, not only the changes in index of refraction, but also the solutions. So we start with an ansatz. So we have L right here. We imagine that this operator is a first order differential operator in X. We have a function U that is going to be the most relevant section of the technique. We ask to have a system governed by this Schrödinger equation. We don't know the potential V1, but playing with the equations, we arrive to the shape of the new potential, and we obtain a condition for the function U right here. The first condition is that U has to be a mathematical solution of the first system. So in our case, a mathematical solution of the free particle. Second condition is that U must never vanish, because if U is 0 at one position, we will have a divergence right here, and it will be difficult to understand this as a change in the index of refraction. Finally, we added the condition to finish with a PT symmetric potential, and here we notice that since nobody was talking about PT symmetry in 2 dimensions, there was no a standard definition for the operator P. These were the most popular or the obvious choices: Px, just changing x to negative x, and P2, changing x and c. Both are coordinates. So we studied both of them. The operator T is the same operator. And we had a new condition a new condition that we have to satisfy. These are 2 complicated conditions. One if we want a Px T symmetric system, and the other if we want a P2 symmetric system. So this was the most difficult part, to find solution of the free particle satisfying this. We play with these equations, and after weeks, we understood what kind of solutions we needed. So the first solution that I want to show you is this one. This is a superposition of two solutions for different energies of the free particle. They are mathematical solutions. They are not square integrable, but they are useful, because with that solutions, we were able to build these systems. So we have right here a waveguide. This is the real part of the changes in the index of refraction. Over here, we have the imaginary part of the changes of index of refraction. So we obtain a PT symmetric system. We also obtain the solutions. The light traveling inside this waveguide behaves like this. So we have, at one moment, more energy in our waveguide, then we lose energy, then we obtain more energy, lose energy, but everything in a balanced way. Here is an example of another transformation using another solution, another superposition of solutions of the free particle. The waveguide system is this one. Also, we have the real part, the imaginary part here, and the light traveling inside the waveguide behaves like this. we decided to study a little bit more, and we said, okay, we like PT symmetry, but maybe we can forget about PT symmetry and just find new systems. So we break that symmetry, adding here a phase. Well, with this delta, we obtain a non-PT symmetric system that we can study. We can find the solution for this. So this is the waveguide, changing in x and changing in the transversal direction. We have the real part, the imaginary part, and this is how light will travel through this waveguide. And well, the initial problem was with a coupled system of waveguides. Right here we have two waveguides that are coupled. And again, we obtain a system in the way we wanted to have it, changing in x and changing also in the z direction. This is the imaginary part of the changes of index of refraction. And over here, we have two modes. Light will travel in these two modes. One of them, well, this really strange pattern. So this light is traveling like in the inside of these two waveguides. And over here, we have light traveling in the exterior of these two waveguides. So, as a summary, well, we constructed a technique to find solvable, exactly solvable systems of optical settings with complex index of refraction. This technique can be, well, it's a general technique, not only to waveguides, but we have a lot of different examples. And also, this technique is big enough to obtain, for example, Hermitian systems or non-PT symmetric systems and find the solutions. So finally, I want to thank Karina, Vladimir, Mauricio for the invitation. Thank you.
So we have plenty of time for questions. Okay.
Professor, the starting point of your work was with the wave partial equation. And regarding this approximation, I would like to ask you, what is the physical meaning of the partial approximation?
Let me move this. Perhaps like in here. So in this partial approximation, what we obtain in order 0 is the envelopment of the wave. So the wave has a lot of oscillations in the middle, but this is the envelopment of the wave. So that's the physical meaning. There are some also nice, how can I say, reductions. In quantum mechanics, when h bar goes to 0, you recover classical mechanics. And in paraxial optics, when k goes to 0, you recover ray optics. So that's another useful comparison.
Thank you very much.
Any other question?
So I'm wondering about the role that the complex index of refraction plays. So what I'm wondering is, if the index of refraction is real, does that mean that you cannot have something that is PT symmetric, or does it simply make the PT symmetry trivial?
It makes the PT symmetry trivial.
Okay.
Also, you need asymmetric potential, but it makes it make it trivial.
Yeah.
Yeah.
Any other question?
Regarding this definition of Px or P2, I mean, I think the definition of the parity operator is clear that it should be inversing all the special dimensions, right? But I'm wondering which one you use, because you said, I mean, you can use one or the other for your transformation.
Yep.
But in the end, I think which one you use, which is more useful?
It was easier, just because it was easy for us to use this symmetry, reflection around one point. But some of them fulfill both definitions, some solutions. So it was easier to think with this P definition. And also there was a technical problem that maybe, well, you know, that to find the missing state, we needed to use this operator, even though the final system was P2 symmetric for some strange situation. So both operators were needed.
Okay, maybe one more question. If not,
Is there a way to define a PT symmetric Hamiltonian for discrete systems?
I don't know, but I think so. I will think that there is a way, but I haven't seen any article about that.
okay, let's thank the speaker.